So, good evening, everyone. I hope I am audible to you all. Can anybody please confirm whether I am audible? Uh, So, let us begin today's session. I hope even if people join later on, we'll continue with it. It's okay. We waited for 5 minutes already. So, welcome everyone to second session of tutorials on fundamentals of electronic materials and devices. So, as we discussed in last week, this week too, we will be seeing certain problems on the topics that have been discussed in week 1 and 2. So people had requested different topics, so based on that we will be seeing. So I hope that all of you had gone through whatever is given in your previous session. So if anybody has any doubts, can you please ask right now whether you've gone through all videos, and if you have any doubts on specific topic or you want any topics to be discussed later, you can just mention now, or else we can start solving problems from week 1 and 2. Mostly we'll be seeing questions from week 2, but a little bit of week 1 will also be there. You need to be clear with both weeks so that you'll understand whatever questions we are discussing today. So these are my details, and in case you don't have any questions right now and want to contact regarding certain questions or topics later on, you can mail to this particular mail ID, that is sandra.dmrf@gmail.com. So since nobody is responding, I think we can start with today's question. So the first question is, a simplified energy band diagram of an intrinsic semiconductor at thermal equilibrium, that is at 300 Kelvin, is shown. In the accompanying table, which one of the following four columns correctly represents the listed parameters? Assume same effective mass for electrons and holes. So you have to answer keeping in mind that Me is equal to Mh, that is the effective mass of electron is equal to effective mass of holes. So basically you have to answer what is band gap, electron affinity and work fraction based on this particular image that is given to you. So can you first please start trying to attempt, and in case you're not able to answer, I'll be discussing. Yeah. Suraj is unmuted.
Yeah, I'm just going through that.
Yeah.
Uh, I just gone through 1.5 videos of the week two. So yeah,
Okay,
I'll try
fine.
to do my best. Yeah,
Yeah,
not
sure, sure.
completed all, but yeah, let's see what
Yeah.
I can.
Both of you can take a few minutes, and if you have any notes or any other material, you can use that also, just to see. So what is band gap, what is electron affinity, and what is work function? If you know the definition of these three things from this particular image, you'll be able to tell me which of these options are correct. So while trying to answer these kinds of questions, even if you don't know all three answers, if you know at least one answer correctly, you'll be able to like be sure that some options are very wrong. So based on that, you can reduce the number of options you have and finally come to our conclusions. For example, if you see here, most people might be knowing what is band gap directly. So when we have an energy level diagram like this, from this, it's easy to know what is the band gap. So if you know what is the band gap, you can easily rule out two other columns. Only two options will remain. So based on that, only those two options, then you can evaluate for the electron affinity and work function. So
And
that is
that's
one tool. Yeah.
we are not, I'm not able to go through the
Okay.
band gap. Band gap value is something between, right? Delta E1 minus only the between is the band gap, right? The
Yeah.
two
So
heads.
basically, are you telling that, sorry, this is the band gap?
I
Like,
cannot see here.
is it delta 1 or delta E2?
No, it should be between that, right? Delta E2. So I'm assuming that you are, this is the, oh, it's below. Okay, delta E1
Is
is
it,
the,
is this one what you're telling is band gap?
and this is the Fermi level.
Yeah.
Yes, yes, yes.
Yeah. So basically, you know,
Yeah,
okay,
delta
if
E1. Yeah.
delta
I
E1
was
is your
confused
band gap,
when you
yeah,
marked. I could see that below line.
yeah,
Otherwise, I was feeling that it is opposite. So yeah, delta
okay.
E1 is the band gap, and
Then you
electron
can
F.
go, then
Yeah,
your
two.
answer would either be column 2 or column 4.
It is. I'll just go through electron affinity. Electron affinity is something from delta E2 minus delta E1.
Is it E1 or E1 by 2?
Mm,
Like, is it from this point or is it from this point? Is it from 1 or is it from 2?
mm, um, Electron affinity is in the conduction band, right? Whatever is above the
Okay.
above the band gap to the vacuum level.
So basically, you will pull an electron from here till the
Hmm.
vacuum level
Yes,
from
yes,
here.
yes,
So
yes.
basically, it will be delta E2 minus E1 by 2 because we know that this
Uh,
entire thing is even. So
yes.
this is even by 2, right?
Okay, correct. Yeah.
Yeah.
Hmm. Okay, yeah.
Yeah. So So basically, these are the things that you can see in an energy
Hmm.
band diagram. First thing is we have the HOMO, that is the
Maybe
like
one
yeah,
more question
yeah.
before if you go back to the previous diagram. Um, Still coming up. Yeah. So how did you come to know that which is the valence band and the conduction band here? I was assuming the conduction band to be at the vacuum level, end of the line of the vacuum level is the end of the conduction band is what I was assuming,
Okay.
and my earlier assumption, and then it started from the below line, the next dark line there.
Yeah.
So that's what my assumption was. Only then when you pointed out, then I went below and saw that. How did you make that
So
assumption?
basically, the thing is that if you see this particular area, like many energy levels are filled. So we can say that this is the valence band. These two
Hmm.
dark lines are the valence band. So
Okay. Hmm.
conduction band, the thing is that only when there are thermally generated carriers, there will be some part of it will
Hmm.
be filled. The
Hmm.
rest of it will be empty.
So you assumed this is the
Yes.
conduction band
Yeah.
from. Okay. Yeah. Okay. Yeah. Got it. Thanks.
So basically, when you have an energy level diagram, these are the things. So this is the valence band maximum, or the highest occupied molecular orbital. So highest molecular orbital we usually refer to in nanomaterials or very small materials. So that's there won't be any band structure. Instead, there will be individual energy levels. That is when we say HOMO or LUMO. But usually for metals and semiconductors, we go by the name valence band maximum or conduction band minimum. That is these two energy levels, as you can see here. So the difference between these two is known as the energy gap. That is your
What did you
EG.
allude to homo? Just tell me.
Yeah.
What is
Highest,
the full form?
yeah,
Highest?
highest occupied molecular orbital. This one.
Okay, okay, and okay,
Yeah.
lowest
Unoccupied
LUMO.
is lowest unoccupied molecular orbital.
Okay, okay, got
Yeah,
it.
these two.
Mm.
And these two terms we'll usually use only in case of nanomaterials or where the number of energy levels are very scattered, very less. Yeah. So basically, the highest energy level that suppose you have a material, the material is at absolute zero, and in that absolute zero, the highest possible energy level where we can find an electron is known as its Fermi level. So this dotted line is known as the Fermi level. And basically, the Fermi level always lies between the valence band and the conduction band, because all the electrons or carriers, whatever we have there, they will be in their lowest energy state. That is your EF. Basically, EF is your Fermi levels. It lies between the conduction band and the valence band. So the next is this band gap. That is the energy difference between the valence band maximum and the conduction band minimum. This is your EG, or your energy gap. And whenever you want to excite, suppose you have certain electrons here, and whenever you want to excite them to the conduction band, an energy equivalent of to Eg has to be supplied to these electrons in order to excite them from the valence bands to the conduction band. And next we have what is known as the work function, that is WF. So work function is when we remove an electron from the Fermi level to the vacuum level. That is, if you see these two arrows, when you have to remove an electron from the Fermi level to the vacuum level, we call it as the work function.
Oh, that is the work function is from Fermi level. I was
Yeah.
assuming that the work function is from the CBM line where you have to the
Okay.
end of the vacuum level.
Vacuum
That's
level.
what
It's basically from the Fermi level.
Fermi level. Okay,
Yeah.
okay, got it. Yeah.
Yeah. And the energy difference between the bottom of the conduction band and whatever you thought, like from here till here, is known as the electron affinity. That is from here till here. That is the
Yeah,
electron affinity.
yeah, that's the electron. Okay, work
Yeah.
function is from here. Okay,
Yeah.
okay,
Work
got it.
function will be
Okay,
from Fermi level.
Fermi
Electron
level to the.
affinity will be from
Okay, yeah,
conduction band
perfect.
minimum.
Yeah, yeah, that's right. Yeah,
Yeah.
my understanding was correct. Okay,
Yeah.
yeah, I was confused between
Yeah.
these
So basically,
two.
then your answer based on all these things will be column 4. So
Hmm.
delta, this was your delta E1. Delta E1 was your Eg, that is the energy gap, and this entire thing was delta E2. So delta E2 minus half of E1. From starting from here till here, you have your work function. Yeah. So your answer will be column 4.
Yep.
Yeah. So the next question is, which of the following describes the relationship between carrier concentration and the band gap for an intrinsic semiconductor? So they are asking the relationship between Ni and Eg. That is, Ni is your carrier concentration, Eg is your band gap. So what is the relation between them? Are they having a linear relation, a reciprocal one, an exponential one, or a parabolic one? So if you remember the equation
Uh,
for Ni, or if you can just find out from Google or your notes, what is the equation for that connects Ni and Eg, from that you will be able to understand whether they
Yeah,
are having
but
a, yeah,
from a commonsensical point of view,
yeah.
if EG is more, then less the concentration, right?
I would not say, yeah, that is true, but then too, like, what is the ratio between them? Is it a linear one or exponential one? They are not, we are not
Okay.
being asked whether it is greater or lower. Yeah,
Mm.
suppose it is lower, does it decrease exponentially or does it decrease linearly or parabolically?
1 second,
Yeah,
let
you
me
can
see
just check
the
the
equation.
equation. Shivani, am I audible? You can also unmute and speak if you have any doubts or if you have any answers. Please do unmute and speak.
It's directly proportional, and I.
Uh,
1 second.
yeah,
Just,
this is the equation that you have to find.
yeah,
Yeah,
minus 2G. Yeah, that's the same one.
yeah. Ni is proportional to minus Eg.
Minus EG, correct. I didn't see the
Yeah.
minus. Yeah, okay, minus EG. Yeah.
But the thing is that it is e power minus Eg. So we can't say
Mm.
it is linear. Therefore, it
Exponential.
is an exponential relationship.
Mm. Yep.
Yeah. Since there is an e here. It's
Okay.
raised to something. E raised to something, and that something is your Eg.
Mm.
Yeah. So
Yeah.
it's an
Okay.
exponential relationship.
Exponential. Yeah.
So next is, which of the following statements are true? Note that more than one answer might be correct. One first is addition of trivalent impurities to a semiconductor creates many bound electrons. At high temperature, mobility decreases because of lattice scattering. Increase in carrier concentration results in decrease in semiconductor resistivity. Amphoteric dopants always act as donors.
Okay.
Here too, you can use the way where you rule out the ones you are
Elimination. Yeah.
sure. Yeah. So that is best when you have multiple choice and you're not very sure about the answers.
B is correct.
Okay.
Increase in carrier point results in decrease in that's also correct. P and C.
Increase in carrier concentration, decrease in resistivity. Okay. Then what about A and B?
I don't know.
Yeah. So basically, addition of trivalent impurities to a semiconductor creates many bound electrons. Trivalent impurities basically, as per to what we discussed last week, these are electron deficit materials compared to the semiconductor group. That is,
Hmm.
when comparing to group 4, these have less number of electrons. So basically, they don't create an excess of electrons, they create an excess of holes. So this is wrong.
Correct.
A is wrong.
Hmm.
B and C are correct. At high temperature, mobility decreases because of increased lattice scattering. That is true. Again, increase in carrier concentration results in decrease in resistivity. So, greater the number of carriers, more the amount of conduction happens, which in turn translates to decrease in resistivity. Next is amphoteric dopants. Do you know what are amphoteric dopants?
No,
Yeah. Suppose,
I don't know. Yeah.
yeah,
Good.
suppose you take gallium arsenide as your material.
Hmm.
So this is a semiconductor material and you take silicon as the dopant. Silicon is the dopant and you are adding the silicon dopant to your gallium arsenide semiconductor. So if the silicon replaces the gallium atoms, they act as donors.
Hmm.
And if the silicon replaces the arsenic atoms, what happens? They act as acceptors or holes. So dopants which are capable of acting both as donors and acceptors are known as amphoteric dopants. So this is
Okay.
false. Amphoteric dopants can act as both donors and acceptors.
Hmm.
Because silicon lies in between, like if you see the periodic table, silicon lies between gallium and arsenide. So if it replaces gallium, it gas act as donors, it has more number of electrons. And if the silicon replaces your arsenide, what happens? It has less number of electrons and hence it acts as holes or acceptors. So that
Okay.
is what is meant by amphoteric dopants.
I understood the D. Can you
Yeah.
just clarify again the A part? Here you're telling that it is P-type semiconductor, P-type
Yeah,
dopant
p-type
purity.
impurities. Yes,
Okay.
exactly.
Okay.
Yeah, trivalent means p-type. Pentavalent means n-type. Tri
Okay.
is p-type.
And whenever
Pentavalent,
there is tri,
yeah,
it is the holes which will increase. And
yes. There is
whenever there is
pentavalent impurity. It means it is an n-type.
n-type, that is when electrons increase. Okay,
Yes,
got it.
yeah.
Okay, creates many bound electrons of addition is many holes. Okay,
Yeah.
correct. Thanks.
So next is degenerate semiconductors generally exhibit dash. Not more than one answer might be correct. A very high level of doping, no change in Hall concentration with change in temperature, Fermi level in valence and conduction band, dopant atoms with negligible interactions in the semiconductor host lattice. So degenerate, like just like amphoteric doping, degenerate semiconductors are a class of semiconductors that we can obtain by some amount of doping.
Okay.
Yeah, you can just check. Either you can use your online
Yeah.
sources or you can go through your notes and find out the basic general like definition of degenerate semiconductors. And once you tell me the definition, we can go through the explanation for the options.
Okay, so degenerate is more of impure semiconductor is what you told. So I'll
Yeah,
based on that I will try
yeah,
to search the answer.
yeah.
Generally exhibit dash. Okay, a very high level of doping. That is correct. No change in whole concentration with change in temperature. Don't know. Fermi level in the valence band, conduction band. Fermi level in the valence or the conduction band. Yeah, that might be true. Dopant atoms with nuclear. No, I can only point to A and C.
Okay. So we'll see. So basically, whenever we talk about semiconductors, we know the basic definition is that something that has a band gap.
Mm,
Or if you have a valence band here and you have a conduction band here, and there is a sufficient amount of energy difference between the two, we call them as semiconductors. That is, they don't exhibit pure metallic or pure insulator behavior. So whenever we are adding dopant atoms, what happens is that energy levels get introduced in between.
mm,
Yeah, this is what happens when you add dopant atoms. When very high level of doping, suppose that you're adding more and more and it reaches a saturation, all these states become almost filled. So what happens is that One thing is it has a very high level of doping. Next is eventually what happens is that it starts behaving like a metal. That is, all of these becomes possible energy states and it eventually starts behaving as a metal. So there gets more and more Fermi levels get introduced in the valence and the conduction band. So that is the case with degenerate semiconductors. So
Yeah,
basically it converts into a metal.
correct. Yeah.
Yeah. So next question is the band gap of intrinsic gallium arsenide is 1.43 electron volt. Its affinity, electron affinity is 4.07 electron volt. Assuming that the effective masses of holes and electrons at the band edges are equal, what is the work function of your material? Your Eg is given to you, that is 1.43 electron volt.
Mm-hmm.
Your chi or affinity is given to you as 1.07 electron volt. One more condition they are giving is that effective mass of electron is equal to effective mass of holes. And we are asked to find out the work function. So
Okay, so
basically
it
from
is
the previous image, if you remember, work functions means that you are removing the electron from the Fermi level
Fermi level to
to the
the vacuum level.
vacuum level. So, yeah.
Uh,
So there are a set of equations. So based on few equations, you'll have to start solving.
it's
Yeah.
difficult to remember the
Yeah,
equations.
the thing is,
Probably it will be.
EG you have, right? EG, now here you can find an equation that connects EG and ME minus ME and MH. So this is
Let
the thing
me
basically, this is your work function that is starting from
correct.
your Fermi level till the vacuum level, you want to find phi. That is
Yes,
what
yeah,
is being asked here.
correct.
So these are the things given to you and this is the equation you have to use.
Okay.
Yeah. EG is given to you, ME and MH are equal. From that you can get EFI plus or minus, like if you rearrange, you can see EC minus EFI, that is from your conduction band edge to your Fermi level.
Hmm.
Yeah. Till then, can you solve and tell me what is your EC minus EFI?
You want me to solve now?
Yeah,
I don't
yeah.
think it'll take. I
It's fine.
don't
You
have
can
the
take your
data.
time. Even if it takes like say 5 to 10 minutes too, it's fine. So that you get some idea on how to solve. You like thing with problems is that we might feel that we will be able to solve, but last class if you
No.
remember one person told in the final step people get stuck. So you can just try solving, and wherever you get stuck, you can just tell me, and we can start from there.
Yeah, probably. Yeah.
Yeah.
So what is the EC value here? How do I
EC
get
value
that?
is not required. Here from here you can
EF
find out EC minus EFI. You can find out. First, you can tell me what is
EC.
this answer. EC minus EFI.
Okay. K is 300 Kelvin, you said? Or
Yeah, 300 Kelvin.
no, K is Boltzmann constant, right?
Yeah, T is 300 and K is Boltzmann constant.
So what is that number if you can help me?
Boltzmann constant.
Yeah.
Okay, it is 1.38 in 10 to the power minus 23, if I remember correctly.
For 1 point, come again, sorry.
1.38 into 10 to the power minus 23. 1.38 into 10 to the power minus 23.
Okay. T is 300, right? Yeah.
That's
It's
it.
at room temperature, so 300. That's how I understood, correct?
Yeah, T is 300. But the thing is, you have to remember here ME is equal to MH, right? So you need not calculate this actually because ln,
No, ln you don't have to calculate, but
yeah,
you have to calculate ln of me by that you don't have to. I think it should be 1 if I'm not wrong. Ln of 1 is
0.
0, okay.
Yeah, so that
Then
entire
half,
term goes.
yeah, it goes, then it is 0.715.
Yeah, it is basically EG by 2.
Yeah, Eg by 2 is
Yeah.
0.715, yeah.
Now you have EC minus EFI. So if you see the
Mm.
previous, yeah, so this is your EC and this is your EFI.
Mm.
So this EC minus EFI, that is EC minus EFI, this small portion you got is 0.715.
Mm.
If this is 0.715 and if you
Plus
add, yeah,
electronic affinity, yeah.
yeah, if
If
you
you add
add your
that,
affinity, you will get your work function.
yeah.
Yeah.
But how to get this equation? It is too difficult a task
Yeah,
to
I
understand
think
and
probably
remember
it will
this
be
equation.
provided in your examination. I'll
Yeah.
confirm next week, but I think usually it will be given. All these equations will be given.
Yeah, if the
Yeah.
equation is given and this diagram I think is also given in the question, right? Or you,
Diagram, you'll have to memorize. They
yeah,
won't
yeah,
provide
that's fine.
diagram. Yeah.
Okay, yeah. Diagram we can memorize. I
Yeah.
think that's okay. But yeah, I think equation should be, I think otherwise. And LAN, how to use a LAN in that calculator? I don't think that calculator has LAN. Now it was not useful. You have to remember LAN of 1 is 0,
1
but
is 0. Yeah, but
uh,
LAN will be there. Like, only thing is, if I remember correctly, you have to press it reverse because in with your scientific calculator, you first press LAN and then press 0, right? Here, first you have to write press 0 and then LAN. Some small difference is there, but LAN will be there in the scientific calculator. Yeah.
no, it's not scientific. No, you will get virtual calculator,
Yeah,
I think
but
in the exam.
it has an option to expand and it comes
Oh,
to
okay.
us a scientific version.
Okay, okay. Yeah. Yeah, these things we have to understand. Probably one class is required for this.
Yeah, for the virtual calculator, but yeah,
Yeah, probably. I think last time, I don't know.
yeah.
I'm working. I am not in touch with all these things now. So
Okay.
I would least bothered about these equations and all. I just wanted to understand the concept. So that's where
Concepts.
I'm here.
Okay.
Yeah, no problem. Yeah, it's good to solve. But
So basically, when you add these things, you get 4.785 electron volts. That is
mm,
your work function.
yeah, perfect. I
Yeah.
understood the concept. That's fine.
So the next question is two semiconductors X and Y have the same effective density of states for both conduction and valence band edges. That is NC and NV is same for both X and Y. The intrinsic carrier concentration of X and Y at 300 Kelvin are 2.2 into 10 power 13 and 10 power 10 respectively. If the band gap is zero point 0.7 for X, find the band gap of Y. So whenever questions like these are asked, usually it will be something that requires cancelling out terms and usually you'll
Mm,
have to find a ratio. Same
mm,
equation for both X and Y, you'll have to take the ratio. So you have NC, you have NB, and all these are same. They have given NI for X and NI for Y are given to you, and you have EG of X. You have to find EG of Y. So you'll
mm.
have to first you have to identify the equation that connects all these terms, and then write down the equation for both X and Y, and then take their ratio. So most of the terms will get cancelled out.
Correct. I
Yeah.
think there is one equation. Mm, let me see. NC and NV combined, right? And you should have the carrier concentrations also for
Yeah.
both individually. So it should be P and
You have the equations. If you remember the equation for Ni, it has root of Nc, Nv as well as Eg. Everything is there in
yeah,
that.
yeah, NC and root of NC NV exponent of EG upon
Yeah.
KBT. Yeah.
So this is the equation you have to use.
Mm. Yeah.
So can you write down the equation for Nx and Ny, Nix and Niy, and then cancel out and try to move in that direction like by cancelling out terms.
Okay. You have to write it 2 times and
Then yeah,
then.
take their ratio. Nix by Niy is equal
Mm.
to denominator of the first one by sorry, the, suppose I'll write the Yeah, so these are the terms given to you. Ni1 is given. Suppose I'm taking x
Mm,
is 1, y is 2, and Ni2 is given, Eg1 is also given to you.
mm,
And then when you do, Nc and Nv are equal, right?
mm.
So this is how you have to write down.
Correct.
Yeah. So can you just try solving? You'll be left with only the e power eg terms. And if you substitute everything, you'll get like only the thing that you don't have is eg2.
Eg2.
Yeah.
Yeah, I understood.
Yeah.
So
Can you
you,
just try solving?
yeah, I can. So you can give Ni1 and Ni2 values, please. I could not see them. If you can give me Ni1 and
Yeah.
Ni2.
This is like 2 into Ni1 is 2 into 10 power 30,
2 into
10
10
power
power 30,
13, and Ni2 is 10 power 10.
10 power 10.
And Eg1 is 0.7. Nc and V you can cancel in both numerator and denominator.
Eg1 is
Uh, zero point 0.7 electron volts.
0.7. Okay. So it will be probably e raised to minus Eg by 2 kT divided by e raised to minus
Eg by
Eg by
2.
2 kT again. So
Yeah.
you have to put Eg1 and
Eg2 and the
Eg2
values
and
of 2 kT also.
2 kT. Yeah. So Eg1, Eg2. So E can I use 2.71 directly? I think that's the value, right? I searched it on Google.
Okay, yeah, you can use that, I think. Yeah. I think it might work out.
Let me see. Value of E.
But the thing is, in your denominator,
2.718.
yeah, denominator, you don't have Eg2, right? Yeah, so probably there again, you have to take log so that you get your answer. It's e power something, so you have to take log on both sides later
Okay, so I don't have a log calculator now.
on.
Sorry.
Yeah, till then you can
I'm
tell me
working
and
on
I'll
my
calculate
system.
the log part for you.
I'm doing it on Excel, sorry.
Okay, fine, fine. No issues,
I
you
was
can
doing
do.
it on an Excel,
Yeah,
so
yeah.
Boltzmann constant is 3.1 into e raised to minus 21, you said?
23.
3.10 into e raised to minus
3
23.
1.38 into 10 power minus 23. 1.38
1, 1.38.
into 10 to the power minus 23.
So I got it as 1 Eg divided by 2 kT. Okay. Okay, I see your solution.
Yeah.
I think it's taking some time on Excel.
And the units you have to substitute in the same. Suppose you are
Mm,
substituting electron volt, you have to
mm,
substitute your
mm.
Boltzmann's constant in the same.
Same,
Suppose
yeah.
you,
Okay.
and here I have substituted in electron volt itself. That is why my like substitution is different. I have taken as 8.617 into 10 power minus 5 for my Boltzmann's
Mm,
constant. Suppose you're substituting it in joule, then you can use the 1.38. And
got it.
when
Mm,
you're using joule in the numerator, you have to multiply your zero point 0.7 with 1.6 into 10 to
mm.
the power minus 20.
If you use the same, I think if
Yeah,
it's all in electron volts or either all in
yeah,
joules.
yeah,
Uh, got it. I think understood. I think
yeah.
this is more of a math
I
to
think,
solve.
yeah.
I
So,
I would more worry about how to get the equation because I would not be able to remember that equation. If they are
equation.
able to give the equation, then probably it's math after that.
Yeah. So basically your e power value goes as 6.59 into 10 to the power minus 10, right? Then
Mm,
what you do is that you take log on both sides.
mm.
So log of e to the power something becomes that something itself. Only this will remain.
Log 1 second. Log of
E to
e
the power,
raised.
yeah.
Yeah, yeah. Okay. Yeah, then only this remains. Yeah,
Yeah, only the
ln and
Eg
yeah.
by 2 kT
Eg by
remains.
2 kT remains, and then
This
this
you can
side
directly
ln. Yeah,
solve in your
yeah.
calculator, like log of
Calculate.
this value.
Mm, mm,
So
mm.
Eg by 2 kT becomes minus 21.14. And you know
Okay.
K value and T value,
P
if you
value
substitute,
Eg2.
you will get your Eg
Uh,
value.
yeah, I would be more worried about how to convert this LAN and log in that
Yeah,
calculator. I was confused last time. I could not solve that.
yeah. Ln
In the
e to the
fabric.
power something becomes the power
Yeah,
itself.
that I understood.
Yeah,
In the calculator, I think there is log, right? And
yeah,
how do you convert it to LAN in the virtual calculator? That day I was not able to
yeah.
do that.
Usually for this part we use LAN, natural logarithm. We don't go for log.
Yeah, no, but
Yeah.
in the calculator, it shows only log, I think.
Log.
It
Okay.
doesn't
So I'll do
show.
one thing. If possible, I'll try to,
Probably,
yeah,
if
like
you
how
can
to
solve this in the
natural
calculator, you
virtual
can put
one
this
and
here,
try
but
that.
yeah, if you can just put your virtual calculator also next time so that
Yeah,
we see how it happens.
happens. Yeah, sure. No problem.
Thanks.
Yeah. So next is given that the effective masses of electrons and holes in silicon are 1.10 and 0.55 ME respectively, find the location of intrinsic Fermi level at 300 Kelvin. ME is the rest mass of the electron and band gap is 1.1. So basically Eg is given as
Mm,
1.1 and then effective masses of say mass of electrons and mass of holes, effective mass of electrons, effective mass of holes is given as for electron it is 1.10 ME and this 0.55 ME. So based on this, you have to tell where the Fermi level lies. We know that Fermi level lies somewhere in between, right?
mm,
So if this is your conduction band and this is your valence band, somewhere here the Fermi level lies. So what is this value? Is it 0.454 above, 0.54 below, and
mm,
above and below which part?
mm.
So that is the question. So for
Correct.
this, you have to use these two equations are there. So before we already saw this equation.
Yeah, yeah, we saw that, but
Yeah.
how to get to know that this equation is what you have to use because these are long equations.
Yeah.
How to remember them because
So
and I don't think it's an open book, right?
it's not open
No
book.
book.
So how
Yeah.
you can remember is the thing that is asked to you is Fermi level.
Mm,
What connects Fermi level, Eg and Me and Mh? So if the equation is given to you, which equation has all these four terms? That will be your
mm,
equation that you have to use.
mm,
First, write down what all is given in the question and identify what we have to find out.
mm, mm.
So based on that,
Got it.
here we have Me, Mh, Eg and your Ef. So
Mm.
all these
Yeah,
things
yeah.
are there.
Mm,
And
mm.
one more thing, if you draw the diagram, we know that the valence band is involved and the conduction band is involved. Both are involved,
Mm.
right? So from that, these two equations you can use.
So it is EF minus
Yeah,
EV, right? Something you have to do, or EFI minus EC also is possible because
either is
EC,
possible, and either is possible.
EC is the top of the conduction band,
Conduction
right? Or
band, and then
top of the conduction band or bottom of the
the
conduction band?
top of the. So basically, this is the top
No,
of the
EC is the
valence
bottom.
band, and this is the bottom of the conduction band. Conduction band goes in this direction, right? So
Mm,
this is the
mm.
bottom of conduction band, and this is the top of the valence band.
Okay,
You
got it.
can use either equation, but you
But
have to
yeah.
see the sentences properly. If you're solving with
Mm,
respect to
mm,
valence band,
mm.
yeah, then accordingly you have to select the option. So first, can you like here, so it's such that AG is given, these all values are given. Can you try substituting, and you will get some EFI is equal to EV plus something or EC minus something.
Yeah, you see, yeah, that's correct.
Yeah,
Yeah, I can do this.
yeah,
It's pretty simple
yeah,
from the standpoint of what others were. Yeah,
yeah,
let me go ahead and do this.
yeah.
EFI, and I'll calculate only the second part.
Yeah, sure, no
Half
problem.
EG,
Yeah, half EG is basically 1.1 divided by 2, right?
1.1 divided by
By
2.
2.
Yeah, 1 second. Let me open the next. K is again. Sorry, you have to give me that value.
Yeah,
K is
EG here you are using in electron volts itself,
volts.
right?
Yeah, yeah, yeah.
So it will be some 8.617.
8.617
Mm,
raised to into.
wait 1 minute. The
Yeah, no,
exponential part, yeah, I forgot. Let me think.
no, no, take your time.
8.617 into 10 to the power minus 5.
Power minus 5.
Yeah.
Okay. And T is 300. If I
Yes.
ln of ME by MH, right?
Yeah.
ME by MH is 1 point.
10 by 0.55.
Yeah, 1.10. Can you come back? Okay.
Yeah. Is this what you're getting? 0.013438.
1 second. Let me see. Minus 0.5634. The minus term.
Yeah. 0.56. So basically, approximately, we can write as 0.54, right?
Uh-huh.
So basically, your EFI is equal to EV plus 0.54. So if
Mm.
this is your conduction band and this is your valence band, your EF.
Mm.
So this is, say,
No, there
EV.
should be a band gap also, no, in between.
Yeah, this is your
Uh,
band gap. This is your EG. But here they are
okay,
asking where
okay.
is the Fermi level.
Fermi level.
So
Okay,
Fermi
whether
level
it
is here
should
and this
be
was
here.
your
Yeah.
0.54. So your answer will be such that the Fermi level lies 0.54 electron volts above the valence band. That is the correct option.
Fi minus EV. EV is the top of the
Valence band, this
valence
position. Yeah.
band. Okay, okay, okay. Top of the. Okay, that's correct.
Yeah.
Okay,
So the
perfect.
sentence, yeah, the option should be the sentence such that 0.54
Mm.
above valence band.
Yeah, and how can it be the other way around?
Suppose you are taking CV and it will be EC minus EFI, right? Will be
EC
some X value.
minus EFI. Okay, it will be below the.
Yeah. So
Um,
EFI will basically be what? EC minus X. Sorry,
mm, mm,
sorry,
mm,
EC minus X. So
mm.
then the sentence, the other option which is correct is that the Fermi level lies point some X value
X
below the
value.
EC.
Mm,
That is conduction
mm.
band minimum.
So the in the diagram you have written here,
Yeah,
uh, VB is the top of the valence band and CB is the bottom of the
conduction
conduction
band.
band, correct?
Yes, yes.
So always all the equations are based like this only.
Yes, all equations are based like this only.
Perfect. Yeah,
Yeah,
that's what I
and
wanted. Yeah.
sometimes both of these options might be there, and both options will be correct. If you answer
Hmm.
either one, you will
Hmm.
get full marks.
Got it. Yeah. Okay. Can we go to the options to see or not required?
Yeah, it's okay.
I understood the concept. Perfect.
Yeah, we can go back and just see.
Yeah.
Yeah, 0.54 above the valence band. Right.
Yeah. Yeah.
Then point some. If you like calculate the other way around, this might not be 54 or some value you might get. That value below the conduction band
Below
will
the
also be
conduction
correct.
band, probably the D option should also be correct.
Yeah,
Probably,
but
right?
then the thing is, that also will be correct. True.
Yeah.
But here there is a plus value, here minus value, so some differences might be there.
Yeah. Yeah. Yeah.
Yeah.
Got it. Got it. Yeah. Got it. Yeah. Yeah. Just check if this equations and how it'll
Yeah,
be
yeah, I'll ask and confirm
given
you
in the
next week.
exam. Yeah.
Yeah.
I have not booked the exam still, but yeah,
Okay, but
probably
the
curious.
last date is
12th, I think, right?
12th. Okay, fine. Yeah.
Yeah. Just looking how can I really manage. I'm working, so
Okay, if you
I'm just.
like
Uh,
give me your mail ID, I'll check with them and I can send you a mail like whether the
hmm.
equations will be given or not. If you can
Yeah.
please
Yeah.
post your mail ID in the
Sure.
chat box, yeah.
I will mail it to you. I think I sent you a. You are on active on LinkedIn. That works well with me. Then
Okay,
mails.
fine. Yeah, I take
I
them
sent it
once
to
in a while,
professor
but
today.
not
Okay,
much. Yeah.
professor has accepted it
Okay.
because mails are more of you have to go there and check on the
Check.
mail.
Yeah,
So
yeah. Okay.
yeah.
So yeah, I'll check my
Oh,
LinkedIn. Fine. Yeah.
and they get missed because of the spams. But LinkedIn is more of you
Okay,
message
fine,
there and
fine.
it
Yeah, I'll
comes
message
back.
you that. Yeah.
Yeah.
Which of the following materials are considered transparent to visible light?
Which of the following materials can be considered transparent to visible light is
So it's something based on
silicon,
band
right?
gap.
Band gap, yeah,
Yeah.
not band gap. I think it is related to the wavelength of the light it
Yeah.
absorbs.
Wavelength indirectly like, decides the band
Yeah,
gap.
yeah, correct. Band gap,
Yeah.
correct. So I think silica only.
Is it
Silicon is
silica or silicon?
silica is sand, right?
Yeah.
Or it is glass. No, it is sand. Silica is sand,
Yeah.
correct? It is silicon, I think.
Yeah. Okay. So can you give an explanation as suppose instead of this, which of the following materials is visible to light, and instead of giving the names, you're given just a set of band gap values, some different value, four values are given to you. If that is
Hmm.
the case, do you know how to calculate and
Yeah,
tell?
yeah, it is.
Yeah.
I think the equation is. I know the equation. I just did that video, but let me point out exactly.
Yeah.
Lambda is equal to hc by eg,
Yeah.
and if you get lambda below 1060 nanometers, am I right? It's in the visible,
Visible one.
correct?
So basically, this silica band gap is 7.5 to 1.96, silicon is 1.1, cadmium sulfide is 2.42, and gallium arsenide is 1.42. So based
Hmm.
on the equation that you just told me, so this is the equation, lambda is equal to 1240 by E, that is EV in your nanometers. So this is like a
Hmm.
shortcut that we used instead of
Hmm.
separately substituting HC and
Hmm.
all
Hmm.
that. We'll
Hmm.
just
Hmm.
directly substitute here.
Correct. Hmm.
Yeah,
Hmm.
suppose we substitute our 1.12 here for all
Hmm.
materials. We can see that gallium arsenide below 876, cadmium sulfide below 152.
So what does this mean? I want to understand what
Yeah,
does this mean.
that is
Can you
what
come to
I'm,
the
yeah,
question?
yeah, that is
Yeah.
what I'm coming to.
Hmm.
0.12. So for silicon, it will be 1107.14 nanometers. So what it
Okay.
means is that your
Hmm.
material will absorb
Hmm.
everything above this value, sorry, below this value.
Okay. In the sense, this is in the visible region, right? This nanometer is in the
Yes.
visible region.
Yeah.
Okay. So
So since what here,
observe.
yeah. So basically, silicon can absorb everything below 1107. Suppose this is your solar, like suppose you have a solar spectrum like this. So this is
Hmm.
usually how the solar spectrum looks.
Hmm.
Suppose and here you have the value of 1107. This is your
Hmm.
Eg and this is your lambda.
Hmm.
So what happens is that silicon can absorb all of these things. The entire spectrum goes in.
Hmm.
So it's getting
Hmm.
absorbed. But with
Hmm.
silica, the problem is that it is like 165, somewhere very
Hmm.
small. So only the small section is getting absorbed. The rest all are just passing through it. It's getting transmitted.
Oh, okay, okay. Now I understood.
Yeah,
Okay, this is what it means.
yeah,
So when you get the wavelength of that material, the wavelength below that will be absorbed within it, and
yes,
rest all is just passing through. It is
passing
not
through.
doing anything.
Yeah,
It will be more of a transparent.
transparent material. So
That's
that
how
is
I
why
understand.
glass is transparent, right?
Professor gave one example. What does that mean? A glass. He said glass. So he said that glass is transparent. That's what I understood. But how does he say that why it was
So
transparent?
basically, all materials, if you know their band gap, you can see what is the range that they can absorb. If they absorb a
Hmm.
vast range, usually it will be an opaque material. If they don't absorb anything and most of the wavelength just goes through it, it will be transparent.
Okay.
Yeah,
So silica glass is a transparent material. It will not absorb anything. It
yeah.
will just go through it.
Because only
Okay. Got it.
only till 0 to 165 it can absorb. Rest all
Okay.
is
Got
just
it.
passing through. The entire spectrum is safe. You know, it's from like
Got
what
it.
700 nanometers or 7,000 nanometers or something,
Hmm.
right?
Hmm.
That is the thing. The EM spectrum, if you know, in that the visible lies from 400 to 700, right?
Hmm.
So in that 400 to 700, this values already get absorbed. So
Okay.
it is opaque in nature. But here, only less than 165 get absorbed. Rest all just passes through.
So silica here they mean is glass, right? Or
Yes.
silicon dioxide is glass only?
Yeah, silica is
It's
glass.
powdered glass. Yeah.
Yeah.
Okay. The silica is sand also, right?
But the structure, how the atoms are arranged is different. But usually when we say SiO2 silica, it is glass.
Okay.
Yeah.
Okay. Got it.
So
Okay.
next is, and in an intrinsic semiconductor, it is given that
Hmm.
Nc is greater than Nv. If that is the
Okay.
case, where is the
Conducting.
Fermi level located at room temperature? They are asking where is the Fermi level? Is it above the valence band or is it at half, etc. So based on Eg, so you have to find here an equation that connects Nc, Nv, and Eg and EFI. All these four things.
Mm-hmm.
Yeah.
Okay. Let me see there. I think the same equation. One second. I'll give you that equation. Uh, I bought professor's book. That helps me.
Yeah.
I just
Yeah.
thought I'll read
He's
it.
he teaches based on the same book. Yeah.
Yeah, very good book. I like reading books, so I think let me go ahead and read it.
Yeah.
So here I can see an equation. One second. Intrinsic semiconductors. Yeah, there is one equation. EFI. Yeah, where is this equation? Yeah, I got the EFI is equal to EV. Yeah, the same one. Yeah, I got it. Half Eg minus 3 by 4
Yeah.
kT kBT line of.
So, and here they have given that NC is greater than NV. Then what will be the case? If NC is greater than NV, how, like, is it above, below? What can you say with respect to EG?
So EFI minus EV, that's how you do it.
Yeah.
EFI
And one
minus
more thing
EV
you have to
is,
notice here is that all choices are given with respect to top of the valence band, which means that
respect
they
to
are
top of
calculating
the
only from,
yeah,
yeah, only
top,
from this part.
yeah, yeah, so that is top of the valence band means, yeah.
And that one,
So
that means one
but
more thing.
E-
This
EF
energy
minus
level they are
EV is
taking as zero.
0. Mm,
Yeah.
okay. So
Since
this
EV is
this
your
equation will
reference.
give that only, no? EFI minus EV will give you that only, no?
Yeah, the
Top
same
of
thing.
the valence. Top of the valence band. Yeah, top of the valence
Valence
band.
band.
That's correct. Yeah. Yeah.
So this is your EFI.
Yeah.
EFI.
EFI.
And since
Yeah.
your valence band is the reference, this term becomes zero.
0. Yeah.
Yeah. So then what will be the case if NC is greater than NP?
NC is greater than NV. Then it'll be positive. So it will be above EG by EG by 2. It's positive, right?
Yeah. So
So
basically
it,
it is half of EG minus this value will be positive. So it is minus this something, right? So it is EG minus something. So it will be below EG by 2. This is your answer.
Correct,
Yeah.
correct. Yeah. EG.
Yeah.
Yeah, below EG
By
by
2.
2. Correct. Yeah. Below EG by 2.
Right.
Yeah. I thought ln of 1 is 0.
Yeah, but here it is only mentioned greater than. We don't know like whether it is
Okay,
not
equal or
equal.
not.
Yeah.
Ah, okay, okay.
If it is equal,
So
it is
EG,
EG by 2.
EG by 2.
Yeah.
Yeah, yeah. Okay, got it. Yeah.
And one more thing is if they are telling that if it is NC, NV is greater than NC, then what
Mm,
happens is that the denominator becomes greater and
mm,
ln of
mm.
that becomes a negative value.
Negative value.
And
Yeah.
this again converts to plus.
Yeah.
Then it goes
Got
above
it.
EG.
Yeah, this is a lot of math than
Yeah.
the subject.
Yeah.
Okay.
And most of the numericals that you will get in exam will be on similar
Yeah,
lines.
similar lines. Yeah, got it. Yeah, but more of it, I would be worried about the equation. I would
Equations.
not
Yeah.
be able to remember this much at this age now.
Yeah.
41 is too much to remember these things.
Okay.
Yeah.
Yeah.
Okay.
Yeah.
I'm just doing it out of interest.
Yeah, fine,
Just
fine. Yeah, I
coming
think
into.
mine, like, I've never taken up an NPTEL course as a student, so I think that the equations will be given to you. I will confirm it on LinkedIn. I'll check with
Yeah,
them and I'll
please.
confirm it.
Sure. Yeah,
Yeah.
yeah.
So next is for an intrinsic semiconductor, the room temperature electrical conductivity is given to you. Electron and hole mobilities are also given to you. The carrier concentration we have to find out. They have given you the mobility of the electrons, the mobility of the
Yeah.
holes. Conductivity is
Mm.
given to you. You have to find out Ni. There is an equation that connects all these things.
Yeah, there is
Yeah.
one. I know. It
Can you just
is
find
here.
that? Yeah.
Yeah, I can find out equation. I can find out it is here. Ni is equal to Nc. What all you want me to connect? 1 second.
Yeah.
The engineering room electrical conductivity is given. Okay. Conductivity is sigma, right? It is here one. First equation is there. Sigma is equal to Ne nu E plus whole E and mobility nu H.
Yeah.
That's what you want?
Yeah.
Yeah, I have. I got that equation. Yeah.
Like, can you tell me the equation?
Sigma is equal to
Yeah.
N E nu E plus P E nu H.
H. Yeah. Here everything is
Yeah,
given. Only thing you have to
yeah.
find out is Ni. Can you just
And
substitute and tell me?
Ni is nothing but they have removed. They've taken 1 second. N and P are common, so that's how they have got it to nu. See, okay, Ni is common. Okay, they have taken the concentration of holes and electrons to be same. No, they have given that. No, then if an integer room temperature electric conductivity is this much, if the electron and the hole mobilities are this much, okay, mobilities are here this much. Yeah, you have to just find out Ni right here.
Yeah.
You have to substitute and find out Ni. Okay, I can do that. Mm, I'll just put it in Excel and give you. Ni is equal to sigma upon all this divided by this, right? Okay, sigma is 10 raised to minus 6. Just tell me the values of nu E and
Nu is
nu
0.75
0.75
and
and then
nu H
plus,
is
yeah,
0.06.
0.06 and E is columns, right? Some columns. It's given.
Sorry, E is your exponential energy. That is the energy of the electron.
Yeah, the energy. So
Yeah.
it should be in coulombs, right?
Yeah, yeah,
1.9 something.
yeah. That
Where
value.
is that? Where is that? I don't know. What is that exact value?
Okay, it
I
is
would need that one.
1.6 into 10 to the power minus 90.
Okay, 1.6 into 10 raised to
Oh,
minus 9.
90. Yeah.
Yeah, these all are very
Yeah.
to remember.
But I think electron
Little.
value and these constants,
I'll get it on Google.
yeah, few constants might be given in the exam, but some might not be there, I think.
Yeah, it's difficult, I
Yeah.
think. And then to remember and then attend an exam now. So the value is probably, let me know if it is correct. 7.71 e raised to 10.
7.78 into 10 to the power 12 per meter square.
12, huh? Yeah, same. Yeah,
Yeah.
I got it. 7.78. Yeah,
So next,
got it.
yeah. So next is the intrinsic carrier concentration of silicon at 300 Kelvin is given as 10 power 10. A
Mm,
sample of silicon is doped with phosphorus atoms of 10 power 15 and boron atoms of 10 power 16. Assume complete ionization of all dopants. Which of the following is true?
okay.
So basically they have given
Okay.
Ni.
This have still not come still, but yeah, you can go ahead and explain. I
Yeah,
have not read this content still.
content part.
I
Okay.
have just did one and a half, so this is not come.
Okay, fine.
This is, I think, in the third week. I think these problems are given.
Second
This
week,
is
I think.
no
Second week, yeah.
intrinsic. So you've gone to intrinsic dopants, no? Now
Dopants, yeah.
dopants is in
Third week,
the
yeah.
third week, no?
Yeah.
It is more of what you call impure semiconductors.
Yeah.
Yeah, that's I think that is third week. No problem, but go ahead and do it. I would be interested.
So Ni is given to you. Ni means the intrinsic carrier concentration, that is 10 power 10. So, and
Mm-hmm.
here two types of doping they are using. First, they are using phosphorus.
Mm,
So, phosphorus means that it is pentavalent, right?
mm,
Pentavalent meaning that it has more holes, more electrons.
mm,
So, basically,
mm,
that is 10 power 15. And then we have boron, which is trivalent,
mm-hmm.
that is 10 power 16. So, here 10 power 15 electrons were added and 10 power 16 holes were added.
So pentavalent is holes, huh?
Electrons, more
Oh,
electrons.
pentavalent is more
Electrons.
electrons. Okay, how do you remember this?
Basically,
Trivalent is also.
yeah, silicon comes in group 4.
Yeah, I don't want to remember
Yeah,
so much
boron comes in
periodic. Yeah.
group 3.
Okay. Okay, got it.
And phosphorus comes in group 5.
Mm,
So this is penta, this is trivalent, and this is your material. And these two are the
okay.
dopants that we are using.
Okay.
Yeah. So then both P and N type carriers are used here, right? And whenever
Mm,
both types are used, that type of doping is known as compensation doping.
okay.
Yeah. And here the number of holes, that is boron is being added and it is adding some 10 power 16 holes, and
Mm,
phosphorus is adding some 10 power 15 electrons.
mm,
So
mm,
basically we know that this is greater than this part, right? So more
mm,
number of boron atoms are being added, and hence whatever
mm.
we had initially, it gets converted into a p-type semiconductor.
Got it.
And in
Got
that
it.
p-type conductor, the number of carriers will be this Na minus Nd, that is 10 power 16 minus 10 power 15.
Mm,
So P is, now you have the P value,
mm.
and we know that Ni square is equal to N into P.
Okay. Ni square is equal to yes, hole into electrons
Electrons.
into holes.
Yeah, so N will be Ni
Yeah.
square
But,
by P.
got it.
Yeah. So basically Ni square by P, you will get something like 1.1 into 10 power 4.
Okay, I have to go ahead and study this, so
Yeah.
I'm not able to connect to this. But yeah, all the next questions are similar, or
No, I think only one or two questions we have.
okay, we'll go ahead and finish
Yeah.
that then. Yeah.
So next is a similar thing, but here they are adding on, like, this is based on conductivity. Yeah, this is based on conductivity, whatever you solved before, right? So here they
Mm-hmm.
have asked electrical conductivity directly. I think you can
Got
directly
it.
solve since you already have the
Substitute, yeah.
equations. Just
Sigma is
substitution.
equal to. Yeah. Okay, I got this.
Yeah.
Let's not do this.
No,
Yeah.
can you just try and, like, I won't say what
Okay.
all is given, just directly try and tell me which option is the answer. You can read the paragraph
Okay.
and then find out what is what.
The intrinsic carrier concentration of silicon in that tends to minus, and the electron and the whole mobility are this much. Okay. Silicon is doped with 10 raised to 15 phosphorus atom. So Ni is given to me,
Yeah,
10 raised to 10,
yeah, that is your
uh,
Ni.
yeah, and electron and hole mobility is given to me.
That is your
Uh,
mu E and mu
nu
H.
E, nu E, mu H,
Yeah,
and then there is what they want. They want me to find the electrical conductivity.
conductivity.
So I can get directly by this, right?
Yes.
I don't need this. What is the last one? Silicon is doped with
Yeah, that part
10,
you need
not it.
because I give you, just
Mm,
now I give you the equation, right? Ni square is equal to Np. You have your
Okay,
N,
okay.
and whenever you are asked to find out the electrical conductivity of a doped silicon, you cannot use Ni. Ni should not be used. We should use N
Mm,
and P separately. So here,
okay, NNP is equal to Ni square. Okay,
yeah,
got it. So I was coming to the pure semiconductors.
yes,
That is the,
yeah,
yeah. Okay, now I got it.
yeah.
So now it is,
So you have
okay,
your
so
P, you have
now,
your N, and then you can again substitute in your previous equation
how
for
did I get
conductivity.
P? 1 second, let me go
Yeah,
through
sure.
this. 1 second. Mm, okay. So first I have to calculate my Ni square then,
No, Ni
correct?
square is given to you, right? Yeah, like Ni is given, from that you can find out Ni square. Ni is basically 10 power 10, right?
Yeah, but intrinsic carrier, they say when they mean intrinsic carrier concentration,
Yeah,
it means the both holes and
electron.
electrons together,
Yeah.
Ni square.
In intrinsic carrier conductors, we know that both numbers are equal, right?
Hmm.
So they won't
Okay,
be
okay,
specifically. Yeah,
okay, okay. So Ni square is given to you,
yeah.
and divided by N is that
P
you are
value.
doping what P
Yeah.
value? Phosphorus doped, right?
Yes.
Uh, Phosphorus when it is doped, then it is trivalent or pentavalent?
Pentavalent. Phosphorus gives you more
Pentavalent.
electrons. Yeah.
Okay, so when you divide by that, uh, more electrons, right? So now you are getting holes. Okay,
Yeah.
got it. Yeah.
So if you see the value also here, you can see electrons is
Mm.
10 power 15 and holes are much lesser. It's only 10 power 4. Yeah. So
Got
it
it.
is an
Perfect.
n-type
Yeah.
doping. Yeah.
Doping. Yeah. And then doping. Got it.
And now you can directly substitute in the equation you used before, the conductivity
Hmm.
equation.
Hmm.
Yeah.
Got it. Then what they want that they give your answer. So now you have to give them
Conductivity,
conductivity, right?
sigma value.
Yeah.
Yeah.
Sigma value. Yeah. So I have to use this and then substitute that and get the
Yeah.
conductivity. Okay, got it. Understood. Yeah. Thank you. I think I should go through these notes once, then I'll be able to connect to the content also very well. I think you gave me an access today. I saw a mail from you.
Yeah.
I had requested for the
Yeah.
folder access.
Like
Yeah.
last time when I provided it to NPTEL itself, it was automatically giving access to all students. I don't know why this time they are requesting separately to me.
Oh, yeah, I don't know. Okay, no
Yeah.
problem. I work only on the weekends, and today
Okay.
was
The
an
thing is, some
other day where
students
I
they
was
might
working
send
from
a
home.
mail
So,
and I might end up seeing them a few days later. So that could become an
okay.
issue later on, especially towards the exam. Most people
Yeah,
will start asking
yeah.
access.
Correct, correct,
Yeah.
got it. Yeah, I understood this. Thank you so much. I think you
Yeah.
clarify more of my doubts. I am not interested in the exam per se, but I am new to the semi field, so
Field.
I
Yeah.
thought let me go ahead and I'm an automotive guy, and I don't need this. I'm an
Yeah.
MBA guy, but I'm
Okay.
still wanting to
Are you
understand this
planning to do
concept.
any research related activities
No,
or
no, 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 no.
no?
I'm an MBA guy. I did my MBA from Bangalore, so
Okay.
I just got into an electronics field, so I wanted to understand.
But
I did
yeah.
that fabrication. I work with Lam Research.
Okay. So fabrication
Yeah,
part, there is one
equipment.
like I
Yeah,
think towards
I
the
did
next
that.
set. Okay, you did that. So
I
fabrication
finished that.
part,
I
yeah.
did fabrication. I finished
Okay,
first.
fine.
That was there last year, I think. I did that first. Then I saw this course also offered by professor. Then I said, okay, let me go
And
ahead and do
did you
this.
give the exam last time or?
Yeah, yeah. Last time I gave.
Yeah, that
For
was
the
more of a
fabrication, I gave
theory related
theory. A lot
subject.
of
Yeah.
theory and simple math was there. That was good for me. This is also okay. I would be probably stuck up now when it comes to junction and all those things. I am not an electronics engineer. I'm a mechanical engineer. So that's where probably maybe I'll get stuck there. I don't know.
Okay.
Let's see.
Yeah.
The next stuff, right? The MOSFET and all. I don't understand those
Yeah.
things. Yeah.
Yeah. That is like mostly only electronics and electrical people will get to the hold of it.
Yeah, I wanted to know, understand,
Yeah.
but yeah, let's see if
And the
I'll
thing
be
is,
successful.
even in my campus, we have the same course as part of our coursework. But there too, this MOSFET, JFET, and all won't be taught in that depth. Because we are coming from a material science background, and people only
Uh,
specifically working on them require that, right?
No, no, I want to learn this
Yeah,
course.
yeah,
It's
yeah.
more of my interest. I don't want to.
Okay, and then
Certificate is secondary for
yeah,
me. I
then
wanted
the
to
thing
learn
is
this.
whatever lectures this being uploaded as part of NPTEL, surely they'll be very useful if you want to grasp the
Yeah, yeah, very
subject. Yeah,
useful. Yeah, correct. Yeah,
yeah.
very nice. I think I don't want to give any gate and all. My
Okay,
time is done. I am always working now.
okay.
I'm working in this semi field for the last 1 year now. So wanted to learn and understand how things
How
happen.
things
I'm not
happen.
a
Yeah, yeah.
Yeah, that's it.
And
Otherwise,
may I ask which company you're working in?
I'm working for a company called Lamb Research. I don't know if you know that
Okay.
company. It makes applied materials.
Yeah, yeah, I know, I know.
It's similar to that. Yeah, it's a competitor to that.
Okay,
Lamb
fine,
Research
fine.
is a competitor to that. Yeah.
Yeah, so you do you manufacture or it's
Equipments, yeah. We
okay?
manufacture equipments for semiconductors,
Like
making chips and all.
equipments in the sense, like if you we purchase such stuff, so I just wanted to know whether something is useful or not.
No, no, no. I don't know for the lab specifically, but it's all for the fabs where the real chip happens.
Okay, fine,
These are
fine.
all big equipments.
Oh,
They're
yeah,
very
okay,
huge,
okay.
monolith. Yeah,
Like supply line
mon-
based things.
yeah, yeah. All supply chain, all to the plants,
Okay,
manufacturing
fine,
plants,
fine, fine,
which
fine. Not large
TSMC and
scale
all that.
equipments, I guess.
No, 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 no,
Okay,
no, no,
fine, fine,
no, not lab scale.
fine. Okay.
But what is that you're looking for in the
No,
lab?
we usually go for these characterization equipments like UV vis
No, no,
NIR,
no, no,
FTIR, and all
no,
those
no, no,
things.
not that, not
Not
that,
that.
not that.
Okay.
These are all huge equipments which are there for the manufacturing of
Okay.
the chips.
Chips. So,
Like,
like
yeah.
in India, do we have that? Because,
No, 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 we don't have.
oh,
We don't
that
have
is why.
manufacturing.
Yeah,
We
that's
have
why
a
I
technical
asked.
center here. It's all in US and
Yeah,
Malaysia.
that is
But
what,
we have a
like,
technical,
whenever
yeah.
we order equipments, they get delayed a lot. And last time, because of the war, there was a shortage of IC and stuff.
Correct,
Yeah,
correct. Yeah, 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 yeah.
yeah.
We make equipments which makes
Those things,
integrated
yeah.
circuits.
And
Yeah.
last time, many of the equipments that we ordered, it was delivered like very, very late because of this.
Yeah, yeah, yeah. This
Yeah.
exactly. That's where. Yeah. So mine is more into mechanical engineering and stuff, and
Okay.
those things I understand well. But I wanted to understand the end
This
product
part.
also.
Cool, cool.
Yeah,
Yeah.
yeah. Fabrication course was very good. It helped me a lot,
Yeah, like
and I
how
gave that
the
exam.
materials coming
Yeah, yeah,
into place in
materials.
the first place. Yeah, those things.
Yeah, how the fabrication of the chip happens.
Happen.
That helped me a lot because that is where the equipments are used.
Used, yeah.
Yeah, yeah.
Yeah. So next question is,
So
can we
give my
continue?
regards to Professor.
Yeah,
I'm not.
sure,
Yeah, we
sure,
can
sure.
continue. Yeah.
Yeah. So basically, in an extrinsic semiconductor, mobility due to impurity scattering is 300, and mobility
Mm,
due to lattice scattering is 200. So the net mobility, so in we might have learned in resistance equations, parallel connectors, and series connections, etc. Right? Similarly, in semiconductors too, the mobility is due to different factors. One is due to the
mm,
impurity scattering, and one is due to the lattice scattering. And we have
mm,
something known as the Madison's rule.
mm-hmm.
So that particular rule is 1 by mu E is equal to 1 by mu I plus 1 by mu L. That is the total mobility will be the something. Like in case of a parallel connection, the sum of the one that due to impurity scattering and that due to lattice scattering. So
Mm-hmm.
here, so then it's a direct substitution. Only thing in this particular equation, it's not commonly used anywhere, and mostly it won't be included in any sections or any syllabus or books or anything.
Mm,
But there might be a
mm,
possibility of questions coming from this part.
mm.
So that is
In an eccentric semiconductor, the electron mobility due to impurity scattering is this much, and mobility due to lattice scattering is okay. What is the net mobility of the electrons in this
yeah. So
semiconductor? Okay, this
basically,
is
mu
the
I
rule.
is
Okay.
given to you, mu L is given to you. You have to find mu
Oh,
E,
okay.
or it can be other
This
way
is more
around.
of material science.
Yeah.
More of material
Yeah,
science
and
section. Mm.
other thing that can go on in exam is they might give you the total mobility and one of the other component, and they
Mm,
might
mm.
ask what is the impurity scattering.
Got it. Got it.
Yeah, so
Yeah.
it's a direct substitution.
Got it. Yeah.
Yeah,
Okay. I think this was the last question. I have a call at 8:30, so
yeah, we
probably I
can
should.
finish. This is the second. Let me see.
Last. Yeah.
Two questions are there. Is it okay?
Yeah. Let's go for a solution. Yeah. No
Yeah.
problem.
So maybe this question I'll discuss later in the next session because it's something related to integration differentiation.
Okay. Let's do that next session
Yeah.
then. Yeah.
So only that, just the thing is that we have already seen this equation, right? Sigma is equal
Mm-hmm.
to E into N mu E P into P mu H, the one you just used before. Here
Correct.
they are
Correct.
asking what is the whole concentration for conductivity to be minimum. So in
Uh,
mathematics, we have studied that
okay.
whenever you take a derivative and you get equate it to zero, you get a local minima.
Mm.
So we'll differentiate this equation. That is what we do.
Okay. Why are they doing math in this course?
Basically,
This is
like,
not a math course.
but still, everything basically depends on maths and physics, right? So they want, like,
Yeah.
suppose you have the material and you need to know the electrical conductivity at the lowest dopant concentration. Even when we do
Mm.
research, theoretically,
Mm.
derivative will give us the minima.
Mm. Got it. So you're telling consider an electric conductivity, consider the electric conductivity of a p-type semiconductor at low dopant concentration, which conductivity is given by this. At what whole concentration will the conductivity be minimum?
Yeah,
Okay, they want to understand at what conductivity concentration of the whole concentration the conductivity
will
is
be
at the
minimum.
minimum.
So
Okay.
what is the P value such that sigma becomes minimum?
Got it.
So this P, like some one of these options after deriving, we'll get. So the
Okay.
derivation is a bit
How do they ask this question in the course that exam there? I don't know.
like that part. I
You
think
cannot differentiate and all. You cannot do that, right?
yeah, yeah. But if you know the basics of differentiation, we can do this very easily.
Okay.
Yeah, just only the basic
Yeah.
principle, like what is the differential of one
Okay.
by x or say
Yeah. Yeah.
x into a, etc. Only those things. So that explanation I will deal with in next class. And so
Okay.
yeah, differentiated part goes to something like this, and once
Mm,
differentiated, we equate it to 0.
mm.
And
Okay.
on solving, we'll get the final answer. That is P is equal to Ni root of mu e by mu h. At that value of holds, your conductivity will be minimum.
Mm.
Yeah,
Okay.
yeah,
Got it.
yeah. So this is just a direct theoretical question. Consider the semi-log plot of carrier concentration versus inverse temperature. That is, carrier concentration is Ni versus
Mm.
1 by temperature. For an intrinsic semiconductor, the slope of the plot is proportional to dash.
I think it is band gap. Uh, I think I read that course in
Okay.
professor's book.
So
One
basically,
second.
this is
This.
your equation, right?
Mm,
If you're trying to connect, since we are short on time, I'll just explain, I think.
yeah.
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 So here you have your carrier concentration, which is your Ni, and you
Mm,
have your inverse temperature. So based on that, you identify that this is the equation we want to work with.
mm,
So they are asking, it's a semi-log plot. From that, we can understand it's a straight line.
mm.
Equation for a straight line is y is equal to m into x
Mx
plus
plus
c.
c.
And here
Mm,
your m is your slope.
mm,
And here y is your carrier concentration, that is your Ni, and x is 1 by t.
mm,
Right. So what we do is we'll take log ln on both sides.
mm.
We know that ln a into b, that is ln a into ln b is equal to ln a plus ln b.
We got it.
Yeah. So here when you're taking ln, so basically this becomes one term and this becomes the next term.
Mm,
So then if you compare with y is equal to mx plus c, this is your intercept, second term.
mm, mm,
1 by t is your x.
mm.
So your slope m is minus Eg
Minus
by
by
2
2
kb.
kbt.
So
Kb,
then the
correct.
slope is proportional to your band gap.
Band gap,
Yeah,
yeah. I read this. There's a direct question in the sense.
yeah,
There's a direct graph given. So
given
that's where the professor mentions here
yeah.
in the graph saying that in the textbook it is the band
Band.
slope is the band gap.
So how
Uh,
the
mm.
explanation for it is comes from
Yeah,
this
yeah, got it.
equation. Yeah.
Perfect. Yeah. Perfect. I think you did it very well. So let me go through this once again. One second. Give me
Yeah, sure, sure,
10
sure.
seconds. Yeah, got it. Perfect. Thanks.
Yeah, this is the
Okay, so what?
final question.
Yeah, go ahead.
Yeah, so basically, molecular
Molecular.
orbitals are filled in the order of increasing energy. Which of the principle does not govern the filling of molecular orbitals?
This is there in the one this thing also. I was confused. I wanted you to. This was one of my questions.
Okay.
Can you explain each of these laws?
Yeah, sure. So first is Hund's rule.
Mm,
Hund's rules means that whenever you have orbitals like 1s, 2s, 2p, we go on filling like these are filled separately. We
mm,
don't go with the rule for s orbital. Since we know that a p orbital, we always draw like this. We'll first singly fill them before doubly filling
mm,
them.
mm,
So we don't go, suppose you have say 1, 2, 3, 4, 5, 6, 7 electrons in total. So 1, 2, 3, 4 is given. Rest you have 3 electrons here.
mm,
We don't go by filling first box one by one. First, we have to singly fill all the separate boxes. So this
mm.
is correct. We don't go for this thing. That is, you fill one spin here, one spin here, this one. So this will stay empty, right?
Correct.
That is not allowed according to the theory. Like underlying principles of chemistry, this Hund's rule states that we have to first singly fill them before doubly
Got
filling
it.
them.
Okay,
Yeah,
got
so
it.
that is Hund's rule.
Mm,
So next we have, I think, yeah, Pauli's exclusion principle. Pauli's exclusion principle from chemistry say that, so like whenever we are filling an orbital, we know some things that are known as quantum numbers, right?
mm.
And
Yeah.
these quantum for any two electrons, the same atom can have identical values for all four quantum numbers. So there are basically four quantum numbers, and Pauli's exclusion principle states that no two electrons, if you are comparing two electrons, they cannot have the same quantum numbers.
So can you explain what do they mean by quantum number here?
So
I didn't
quantum number
understand it.
means that one thing is this SP, these letters will
Uh,
be there,
uh,
right? Based on their
uh,
arrangement.
uh,
Next is these numbers,
uh,
1, 2, 3, and so on. There will
uh,
be so
uh,
then if you have the nucleus here, how they are filled like this. So
uh,
this is
uh,
one type of quantum number. Then
uh,
filling them into SP, etc. is the next one. And the final one is
uh,
spin. So this is one
uh,
spin and this is the another spin. So whenever we
uh.
are taking two electrons, these four values cannot be the same.
Okay,
Yeah.
got it.
So what are the different quantum numbers? I think it will take a lot of time to explain. So can we explain since you have to go at 8:30?
Yeah, yeah,
Yeah.
we can do this next time, or probably I will. Yeah, next time. When is the class?
Again Monday in 7 to 9.
Monday's 12th, right?
Yeah. Or whenever you're
Okay.
joining, maybe I can keep a note of it and then we can explain simply what is this quantum number
Yeah,
thing.
that is good. Yeah, if we can do that tomorrow, I'm available tomorrow this
No,
time.
since it is part of an NPTEL course, I'm supposed to take only on the fixed schedule.
Okay,
Yeah.
fixed schedule. Okay,
Yeah, yeah, yeah.
okay, okay.
Yeah, so basically the
Got
thing
it.
is all four quantum numbers and spin should not be the same. That is Pauli's exclusion principle.
Mm,
Yeah.
mm.
So next,
Okay, got it.
yeah, then comes the Madelung rule. So if in basic chemistry we know that filling order, suppose we have 1s, 2s, 2p, 3s, 3p, 3d. The order is first
Mm,
we'll fill 1s, then 2s, 2p, then 3s,
correct.
3p, 4s, then 3d.
Mm,
So this is
mm,
the Madelung's rule and Aufbau's principle.
mm.
These both. So
Okay,
this also
got it.
decides how we have to fill electrons. And final one is
Mm,
Heisenberg's uncertainty principle. So according to quantum mechanics, we cannot predict exactly both the energy
mm,
and momentum of anything. That is what Heisenberg's
mm,
uncertainty principle states.
mm,
Yeah. So quantum mechanics, what usually does is that it says that everything has both a wave and particle nature, right? Yeah,
mm.
because of that, we cannot predict exactly the position and momentum of anything in space. Exactly, we
Okay,
can't say.
cannot.
Yeah, this is like it is associated with formation, but it has nothing to do with filling.
Mm.
Filling only depends on this Aufbau principle, Hund's rule, and Pauli's exclusion principle.
All is expression. Okay, so this is the answer
Yeah,
then.
Heisenberg's uncertainty
Uncertain.
principle. These are all important, but Heisenberg
Mm,
it decides
mm.
formation of molecular orbital, but not on filling of molecular orbital.
Got it.
Yeah,
Okay.
yeah.
I think if you can, this content is there, right, in
Yeah,
the
yeah, I'll
folders you
upload
shared.
it. I'll upload it.
Yeah, I'll go through that, but next time
Yeah,
if you can
I
explain me
can
these
explain these.
rules a little bit
Yeah,
more,
in detail, I
that'll
can
help.
explain the rules and I can
Yeah,
discuss the question that we left out, the differentiation question that we left
sure.
out today. Both these things I can do.
Yeah, next Monday we can do.
Yeah,
Yeah.
sure, sure.
Perfect.
Yeah,
Yeah.
thank you for joining.
Thank you so much.
Yeah,
Yeah, thank you.
yeah.